Okay, everyone. So it is now just after 8 a.m. Pacific time. It's time to get started. We're really looking forward to today's TinyML talk. So hello, everyone. My name is David Sawyer from DeepLight. I'm very excited to be hosting today's TinyML talk from the global group to maybe have the topic on-device model fine-tuning for industrial anomaly detection applications from Konstantin Meshcheriakov at Klika Tech today on Tuesday. I'm joining from Montreal, Canada, and we have Constantine calling in from Poland. Welcome, everyone, from wherever you are. Good morning, good afternoon, good evening. Let's get started. So first of all, a big thank you to the TinyML Talk strategic partners. We have an excellent group of companies here: Aeon Devices, ARM, DeepLight, Edge Impulse, EMSA Visual Sense, PhotoHub, Greenwaves Technologies, Gravity Inc., HotG, Imagimove, Itemirs, Klika Tech, Latent AI, Maximum Integrated Analog Devices, Micro AI, NXP, Prophecy, Qualcomm, Kixo, Reality AI, Renesas, Reekson Technology, SAP, Seed, SenseML, Sony Semiconductor, ST Micro, Stream Analyze, SynSense, and Sentient. There are additional sponsorships available, so please contact Olga at TinyML if you're interested. Thank you again to the sponsors. A couple of really exciting notifications here just around the corner. So for TinyML Summit 2022, it is back in person at the Hyatt Regency San Francisco. So there's already, a great group of companies attending. That is March 28th to the 30th in person. And as part of the summit, the Best Product of the Year and Best Innovation of the Year awards are open. Nominations will close March 14th. So there's about a week left to submit for that. And yeah, you can scan the QR code here to register. Again, it's in person, which is super exciting for the summit. And co-located at the summit will be the TinyML Research Symposium. So this will be on the first day, the same day, March 28th. You can register for the link here. That'll also be in person at the San Francisco Airport, Hyatt Regency. And more sponsorships are available. So you can contact sponsorships here to participate in the summit and the symposium. Really, really looking forward to that being back in person. As well, you may be familiar, but for those who aren't, so there's also the TinyML Trailblazers series. This is a really cool and unique series hosted by Chris Rowan, where different founders, investors, participants in the TinyML community will be interviewed by Chris on a podcast, the Tiny Trailblazers series, as it's called. The next speaker will be Eric Pan, is the founder of Seed Studio. So you can register there from the QR code there. That'll be live online April 6th at 8 a.m. Pacific. So a couple of things you may be familiar with. So these are rapidly growing still, which is really cool. There's the TinyML Meetup Groups. So those are all across the globe in 43 groups in 34 countries now. I think there's even more than like 8.5K members. There's like 10,000 plus now or something. It's probably growing by the time we're done this talk. But this is really cool. You can join the Meetup Groups there depending on where you are in the world. And there's also the LinkedIn group. So there's the TinyML community on LinkedIn with, again, people from all over participating, which is really awesome. And there's the 2 QR codes there. So if you want to register or haven't done so already, the QR code for the Meetup group and for the LinkedIn is there. A couple reminders as well. So you can subscribe to the TinyML YouTube channel for updates and notifications, including this talk here. So basically all the talks, are available on the YouTube. This will be available shortly after we go live here. And again, thank you for everybody joining us now as we're getting started here. So you can also find the talks online, and there is a lot of great videos there. As a heads up, the next TinyML talk will be Tuesday, March 15th. That's next week. From Matthias Hertel, who's a product specialist at ARM. The topic will be accelerate ML development with cloud-based ARM Cortex-M models. That's really interesting. So there'll be a talk from ARM next Tuesday. The webcast will start as usual, 8 a.m. Pacific time. And please contact the talks at TinyML if you're interested in presenting. All right, so now for the main event, we're really excited to have Konstantin Meshcheriakov present. Konstantin is a solution architect at Klika Tech with strong experience in building embedded and machine learning solutions. He's working closely with the clients. He's responsible for the architecture creation and initiation of new IoT and ML related projects. He also leads the machine learning competency and internal courses in the company. Thank you, Konstantin, for joining us today. We're really excited to have you present for this TinyML talk. and I'm going to hand over to you now for your presentation.
Okay, thank you very much, Davis. So I'm really excited to be here. And first of all, I would like to introduce our company. We are at Klika Tech, design and develop end-to-end IoT solution. We do design, development, deployment, and we supporting customers in each and every type of IoT applications. Historically, IoT meant embedded and cloud and everything besides between them. So during this time, we were focusing on multi-architecture embedded cloud native serverless applications, delivery of every backend and data lakes and API and enterprise integration, mobile, user UI UX, and everything that was connected with IoT. So we have strong experience in embedded devices, MCU, DSP, and so on. We experienced in creating Git-based solutions in Linux, of course, cloud-based dashboards, processing, and so on, and of course UI, every type of UI. We also have multi-cloud expertise. We are proficient with AWS. We have experience with Azure, Alibaba, Google Cloud Platform, you name it. We are also AWS consulting partner in IoT competency, IoT core, and other services that are connected with IoT. Of course, now IoT also means that we have a lot of data that needs to be processed, analyzed, and taken for the decision making. And to do that, we added big data and AI/ML competency to our portfolio. So we are employing the next wave of innovations by analyzing patterns and trends in data sets to drive business insights and outcomes. We have a lot of partners, software, hardware, and even communication. For example, AWS, Altair, Aero Electronics, Avnet, Develka, Espressif, Flora Alliance, Infineon, Intel, Lenovo Multitech, Microsoft Azure, NXP, Nordic Semiconductor, OnLogic, Quectel, ST, Sci5, Sierra, Syntec, Telefonica, T-Mobile, Technicolor, Verizon, Alibaba Cloud, Vodafone, and Wirepass. And with one of our today, I will talk about one of our projects that was developed with our partner Infineon. This project is connected with industrial predictive maintenance. So before I go to the project introduction, I would like to talk a bit about maintenance and its kinds and how it could be improved and give a business different benefits. So first of all, we go to the maintenance type. Historically, there were several types of maintenance. The most basic one is reactive maintenance. It's the type when you wait till the equipment actually breaks, then you go and replace the part that doesn't work. It works very well when we are talking about, for example, light bulb in your room, because there is no damage from not having light for some time. But in industrial settings, it can lead to large losses, managerial losses, and even equipment, further equipment breaking. So to prevent it, we go to the preventive maintenance. Preventive maintenance is performed based on some maintenance plan. So, for example, the manufacturer of the equipment provides the estimated useful life of its parts and the plan for replacement. And during specified periods, service people go and replace these parts. This allows to reduce the time that the equipment is not in operations. It allows you to plan this maintenance, but again, there are several different downsides. For example, if equipment breaks before the planned maintenance, then we have the same downside as with reactive maintenance, but we can also replace the part that would work for some time, and that would increase basically costs of operations. And it would be good to know when the equipment will break. For that, a good solution would be to add sensors at monitoring to the equipment and analyze the data that we receive from these sensors to get insights on when and what could break. Then we can plan our maintenance window and send servicemen to replace the detail of the part only when it is really needed. The next part, the next step from predictive maintenance would be prescriptive maintenance, when the analytics model, the machine learning model, tells us not only when and what parts would break, but also how to fix it. It would prescribe the recipe to salesmen what to do, but I believe that this would require adding additional systems to for example, deep learning models, and it's not yet here. After that, I believe that there would also be another type of maintenance, and that would mean no maintenance at all. You can imagine, for example, something similar to how cloud solutions can heal themselves without any additional service. Probably something will be there in the future, but right now it's not here. We are focusing on predictive maintenance as something that can be implemented right now and right here. And I'll talk now about types of predictive maintenance. There are several approaches that could be taken. For example, we can try to predict the remaining useful life of a detail. So the question would be, how long would it take for a failure to occur? To create such a model, you would need historical data from sensors along with event labels. For example, when the device breaks, a salesman should add an entry to a database that would act as a label and would be used when you create the models. As you can imagine, it is not a really simple thing to collect, because you will need to deploy the fleet along with the sensors. You would need to operate for some significant time, because these events quite rare. Here we have several assumptions. For example, that the remaining useful life can be modeled, and we can only predict one type of failure with a given model. Of course, there can be multi-head models that would use the same backbone and different heads for different types of failure, but it's quite difficult to create. And of course, we need accurate labels. The next possible approach would be to predict failure within a given time window. It is a classification task, and it answers the question, will the equipment fail within the next n days cycles, for example, within the next week or month? Again, you would need historical sensor data and their events labels, so you have the same problems with collecting the data as before. But here we can have multi-class classifications that can be used to predict different types of failure. And well, we will need to collect a lot of data for each potential failure. And the third type, the one that is actually easier to implement and that is quite a good fit for anomaly detection, is anomaly detection. It answers the question, is the current equipment behavior normal? To train such a model, you don't need historical sensor data. You don't need events label. You need only historical sensor data, probably with a few possible failures. We can create such models under the assumptions that it is possible to define what is normal and what is not, because anomalous behavior is not always a failure. So for this project, and I will talk about it, we decided to concentrate on anomaly detection and create infrastructure to collect the event data for further implementing other more powerful predictive maintenance solution, predictive maintenance models. So we, with Infineon, created a complex hardware and software, embedded software and the cloud software, that can find anomalies in HVACR, heat, ventilation, air conditioning, and refrigerator units that can be installed both on big industrial buildings, but also in, for example, consumer air conditioner units. The main tasks would be that it would be possible to retrofit any existing system. So we don't want to throw away an existing solution and buy a new one. We would like to support a broad range of sensors because different problems require different sensor set. And we would need near real-time condition monitoring to see what is currently happening with the device, and the near real-time anomaly detection, of course. To do that, Infineon has developed an Infineon Extensive Predictive Maintenance Evaluation Kit. It's a board that connects to XMC for 1700 development board and can be connected to different satellite boards with all kinds of sensors. For example, it could be current monitoring up to 120 amperes for current anomaly detection. It can be vibration and position sensors, airflow and pressure measurement for filters, open-closed lead detection for detecting the status of service leads and understanding whether the device was tampered with or not. It could be whole speed sensors, sound anomaly detection with microphones, all of it. You can also develop your own satellite board with any type of sensors you need, because there are connectors for SPI, I2C, GPU, and other protocols that you can use. The good thing here is that it uses Ethernet cables, so it can be installed on quite big units. You can look at this board at this link. We have developed the embedded software for this board. It's based on Amazon FreeRTOS, just FreeRTOS now, and it provides automatic provisioning system and other useful things. We also have created a cloud architecture, a reference cloud architecture that anyone can deploy using CDK templates in their own cloud after they buy this unit, and see the data that comes from the unit in the nice dashboard. So the data goes over MQTT to AWS AD Core, and then it is collected in S3 bucket through the Kinesis data firehose for further model development. And it is also analyzed in Kinesis data analytics using anomaly detection algorithm called robust random cut forest. I will talk about it in a bit. All the data is also sent to Elasticsearch, now OpenSearch, and can be viewed in the nice Kibana dashboard. You will see this in the demo. So let me talk a bit about the anomaly detection algorithm that is used in Kinesis data analytics. I understand that it's not quite a TinyML related one, but I would like you to understand why we have selected and why have we go the way we went with TinyML. So robust random cut forest was introduced by Juha and Saripta in 2016. It is a sketch algorithm, meaning that it creates some internal representation using the actual data that was collected. So it stores the data to provide some information on statistical properties of the data. And it was designed to work on streaming data. Basically, it is an assemble of specially constructed trees, random cut trees, that are designed to maintain the distribution of data with all operations that can be used with this tree, for example, insertion, deletion, and so on. So how does it work? So first of all, we need to train the algorithm with some data. So when we add a point, we create a bounding box around all the existing point in the tree. And after we have created, we split this bounding box in parts, and we create different branches of the tree. So after we do that some predetermined amount of times, we have this tree with bounding box for different data points, and we are ready to go. We are ready to evaluate and get the anomaly score for new data points. How do we do this? We actually create a new data point into the tree. If the point is close enough to other points, then it won't require changing the tree a lot, because it's more likely would get into some bounding box that already exists in this tree. But if the point is really far from the existing points, it will require changing the tree significantly, and so it would need to be rearranged. And so the anomaly score for this is calculated using the average collisive displacement, which is in fact the mean degree of this rearrangement of all the tree in the ensemble. So here we see a downside of such a model is that we need to actually insert a tree into the model, into the forest to get the anomaly score. And so if we want to freeze the model, we would need to copy all the point. We also see that this bounding box that are stored can take quite a lot of memory. So this algorithm is not a very good fit for TinyML solution, but it works pretty well in the cloud. So after we have implemented and looked at the solution, we understood the constant pros of the solution. The pros is, of course, ease of deployment. You buy the board, you run a script, you get the infrastructure, you see the data from your board. It's also near real-time data visualization and anomaly detection. It takes less than a second to see the actual data in the dashboard. You can also collect the data for new data sets. And after that, you can, for example, combine this data with events log from maintenance from serviceman and create any kind of predictive solution. And as the anomaly detection model is string-based one, and it can add new points to it. It can also adapt to the changing environment of customers' infrastructure. Cons here is that infrastructure and data transfer costs a lot. You would need to have either wired or wireless connection. And of course, you will need to deploy all this infrastructure, all this anomaly detection data analytics into your cloud. And another problem is that it is necessary to train that cloud anomaly detection algorithm. So this random cut forest would work only after we have filled all the trees, and if we send data not quite often, sparingly, then it would take quite a lot of time. So right now, or I can answer the questions about this cloud solution.
Perfect. Thank you, Constantine. So there is one question here, first of all, and this is a super interesting in case. So please, everyone, now's your chance to ask more about this predictive maintenance solution. So the first question, Constantine, it's from S. Wang. Is this anomaly detection algorithm supervised based or unsupervised based?
It is unsupervised based. So it just stores the data and some data, not all of that, and it maintains the distribution of the data. And if we get the point that is out of this distribution, then it is an anomaly point, and we detect that.
Excellent, thank you. So we have another question here from Karanpreet saying, do you make use of an anomaly? Do you make use of any anomaly data to improve performance of the model?
Right now, the model is trained from scratch. So if each time the user is deploying the solution, so whatever the data user sends during this preheating time would be considered as non-anomaly data. After this preheating, the user can see the anomaly score for the new data.
Awesome, interesting. And so another question here from Andres Fernando Munoz Herrera. His question is how to validate the model.
And here it is a pretty difficult question for anomaly detection models, because we don't have the data, the labeled data, which would tell us what is the model, what is anomaly, and what is not. In fact, it is often quite difficult to understand for people what is anomaly. There are some statistical methods, and I can answer this question on the forums, but it's quite a complex topic.
Awesome. Yeah, it makes sense. And then there's a few different ways to look at that. There's a couple of questions, and this was actually something I thought was interesting, Constantine, but your use case was the interrelation between the cloud and of course, you're at the very sensor edge here being TinyML and how you've integrated the two for the solution. So there's a couple of questions here around, the cloud. So one of them is from Philippe Lejeune. It's what's your monthly Amazon bill?
That's a really good question. And our monthly Amazon bill is quite large because we have different projects. But for this solution, you would, in the minimal, pay like $50 for the EC2 instance that hosts the anomaly detection model in the data analytics, and not much more for everything else. So
yeah,
figures are about this.
Okay. Thank you for that question. Rick, there's a question from Rick Pandy in the group. I'll put it in the Q&A. The question is, do you also do back propagation on the hardware, on the edge hardware?
Yes. Now, yes, we do that. But I will get to this a bit later.
Awesome.
So, okay. Are there any other questions?
There's a few more. It depends if you want. We can go through them quickly, or if you want, we can at the end.
Let's move on, and then we can address them in the end.
They will be addressed. Awesome. Thank you.
Sure, of course. So we've seen these problems with the cloud solutions. It works great, but it could be improved with TinyML, and so we decided to do that. We have looked at the possible anomaly detection algorithm in the that can be implemented in tiny board for microcontrollers. There are some. For example, it k-means, it DROCC, dprobust one class classification from Microsoft's Gmail, it one class SVM, and others. Most of them comes from classic statistics, and so they require to understand how they work. They require to understand how they create this decision boundary, and how to prepare your data and preprocess the data so that it would work well with this specific data distribution. You can see the different model treat different data distributions in a different way. For example, some of the models would work with several clusters, several modes of the data distribution, but they won't work, for example, if these modes have different density. And other models have other restrictions. That's why we have decided to go with neural networks, because first of all, they are more familiar to typical developers. They are easier to implement right now. We have a lot of tools to do that. We have optimizers from different hardware vendors. So this is quite a good thing to do. And we have decided to use the autoencoder algorithm. What is it? It's a neural network. It can be a deep or shallow network with a bottleneck layer in the middle. So basically what this model tries to do is it tries to recreate inputs out at its outputs. When the data goes through this bottleneck layer, it's of course is compressed, and it's a lossy compression. So the network is trained to recreate only the data that it's seen before. So any kind of anomalies, any kind of unseen data would be reconstructed poorly. And this reconstruction error is basically can be used for anomaly detection. So anomaly score is calculated as mean average error between the inputs and the outputs. Quite a simple thing to implement, and it works pretty well. Now I will show a demo with actual hardware, and you will see how it works on the TinyML. So here in the lowest right corner, you see the equipment. It's a air conditioning unit. You can also see data from different sensors, temperature one, and so on. You see the current operation mode. I will return to it later. Anomaly score, and whether the model is adapting right now or not. Right now it is not. So now we will introduce the anomaly. We will emulate the exhaust clogging. So we will see some problems with air pressure. And you see that after we have prevented the air from going out, we see quite a big jump in the anomaly score. So it works on the device itself. Okay. So do you have any questions here about what I have described right now?
There were some questions remaining from the previous section, but one question I think came from this demo here was, are the sensors wireline or wireless? And if they're wireless, what about their synchronization?
They wired. They are all
Okay.
wired. Yes, because otherwise we would need to add wireless chip on each sensor, and it would work less reliably in the industrial settings, and of course it would make solution really costly. Okay.
One other question, Konstantin.
Yeah, sure.
Sorry, there's another question here that related to the NN approach. So the question is from Karanpreet: does NN approach perform better than robust random cut forest approach?
Yes, it works better, but I will describe why a bit later. But right now, we see like much bigger anomaly difference in anomaly score for the same anomaly when we use autoencoder versus this robust random cut forest. So it is harder to understand whether it is anomaly with robust random cut forest, and it's much easier with autoencoder.
Perfect. And two more quick questions on the demo. This one's from Bing Wang. Is the demo using RNN, so recurrent neural network?
No RNN at all. Only autoencoder.
Okay. And a question on the autoencoder, is the autoencoder trained only with data without anomalies?
This training data has some anomalies inside, but not a lot of them.
Awesome.
So you can mix anomalies into your training data. The data doesn't have to be really pure, but it will still work. Okay, so when we have moved to the TinyML solution, we have lost one important thing from the cloud one. And it is constant model fine-tuning and training. And it's really important because there is such a thing as a concept drift, which can occur when the distribution on the data with which the model is actually used is different for some reason from the distribution with which the model was trained. It can be caused by sample selection bias, for example, when you don't collect your data with a lot of rigor, and it can also be caused with non-stationary environment. For example, it can be environmental change, global heating. It can be non-repeatability in manufacturing process, which cause sensors to give quite a bit different outputs. It can be hardware modifications of the equipment, for example, replacing an air filter with another type of one, and it can be also user behavior changes. So it is quite important to periodically retrain your model with newly collected data. There are different approaches to do that in the cloud. You can collect the data continuously from your devices and then deploy new models using the OTA process. You can use something like model fine-tuning right on the device. Federated learning also can be used. And for this type of model fine-tuning on the device, there are not a lot of papers, quite a few one. It's tiny machine learning for concept drift by Di Sabato, Simon, and Manuel Raveri. Keihan has published TinyTL, reduced memory node parameters for efficient on-device learning. It was introduced on new RIPs. And another one is TinyML, TinyML with online learning for on microcontrollers by Ren and How. I hope I pronounced it right. And we have decided actually to implement this last paper on our TinyML device to see whether it is possible to fine-tune the model right there. How did we do that? So your model should be in the TensorFlow-like format before you can use this library we have created, HTNN. You convert it to as usual TensorFlow model to TF-Lite model, and then you deploy it to your device in the usual way. So, for example, you create an H file with the model, and you link with your code with that. Then, during the first boot of the device, our HTNN model editor can separate the model to the frozen and trainable parts. The frozen part is continued to be stored in TF-Lite format, so that it can be used with TF-Lite interpreter, and it's just a plain TF-Lite model. The second part is trainable layers part. It is stored in the custom format, and it is used by HTNN interpreter. It's actually something that we can train using backpropagation. So in the during the device operation, we get the data, we put it through HTNN interpreter, It calls the TF-Lite interpreter to run the data through the model backbone, the frozen model backbone. Then it gets the result and sends the result to through this trainable layers, and it gets the actual anomaly score. When we enable the fine-tuning, it would also run backpropagation on this custom trainable layers and store them in the device flash. So here is the demo of how we actually train the model on the device itself. Okay. So you can see we have an anomaly, and now we enable the on-device fine-tuning. You will see here that the model adaptation starts, and we see the steady decrease of anomaly score after that. It will get to the same levels that were before we introduced the anomaly. Basically, we will see the model to perfectly adapt to new operational and conditions. So, for example, one use case would be when the technician replaces the air filter with a new type, and we would see an anomaly, but we know that it is not an anomalous behavior, so we can retrain the model for this new filter type. Another thing that we can do with that is on-device manufacturing tuning when we want to adapt to the sensor specific, the model to the sensor specifics. Okay, I am ready to answer questions about this demo and the previous parts, if there are any.
Yeah, absolutely. So we do have a lot of questions here. So we'll try to make sure that we get to all of them, and all the ones that don't, just remind everyone to be addressed in the forum. So one of the questions about this one, Constantine, is the Edge TNN microcontroller dependent?
No, it uses only Eugen library for this backpropagation and nothing more. So it is written in pure C++, so it can be deployed to any microcontrollers or MPUs or whatever.
Cool. Nice. That makes sense. And also a question about, I believe this demo is, do you fine tune the model with just new normal kind of data?
Yes, currently, yes.
Okay, awesome.
Okay. And the last, I suppose, part of my presentation is another thing that we have seen in this experiment, and it is catastrophic forgetting phenomena. So what is it? It's a tendency of a neural network to forget previously learned data and previously learned information when learning new information. So for example, if we have our device that can work in different modes, and we retain the model in one specific mode, it would start to work worse, to perform worse on another mode. There are several methods to avoid it. It can be a rehearsal or pseudo rehearsal. It's when we maintain some samples of the data from different modes on the device, and then we mix them with new data when we fine-tune the model. Or a pseudo rehearsal, probably it's quite similar, but we don't maintain the actual data, and we somehow use the information that is stored in the model itself to do that. And then we have orthogonality. It's quite a simple approach when we have different model paths for different modes. And so this path for modes that we don't train with are not affected during the training. And it's basically what we have implemented here. There are several different methods. For example, it's weight penalization so that new learned weights are not too far from the weights that were trained during the initial training. So the model would work on all kinds of data we used during the training well, and it would adapt to the new data. But basically, we went with orthogonality, and with our approach, doing this is quite simple because we have separated the backbone and the head. And if we know the current mode, we can just use and fine-tune the head for a specific mode. This is basically the same as if we would have several model heads in the model and the input, but it is much easier to implement. So we just like juggling with these model heads when we switch the operational mode. So that's about catastrophic forgetting, and the next steps is with a library, it would be to change the architecture of the library to provide support for any inference engine. Right now, we support only TF-Live interpreter, but there are a lot of tools from different hardware vendors and TinyML platforms that would be also great to support. Then we don't currently have quantization support, and we would like to add it. We don't use any hardware-specific operations right now, but Eugen supports it, and so we would like to also add these operations, and we would like to support additional operations. Right now, we support fine-tuning only for fully connected layers. And there are several cases where convolutional layers would be also beneficial to have. For example, we can use convolutional autoencoder for anomaly detection, and it would work better because it wouldn't rely on the position of the anomaly in the time window data. It would work with any data in which the anomaly happens in any part of this window. So this is further steps. And I suppose that's it. I would be glad to answer any questions that are left.
Fantastic. Well, first of all, thank you, Constantine, for a very, very interesting presentation. And a lot of relevant stuff to the different types of machine learning models deployed at the sensor edge. So thank you for that. We'll go through the questions here as much as we can. So first question, I think, relates to the first discussion you gave on the Infineon product. It's from Mark Donaldson. Would you consider using AWS Greengrass versus AWS IoT Core? Is there a pro-con for using IoT Core versus Greengrass?
Yes, we used the Greengrass. Of course, it would require additional hardware, additional gateway. And in this evaluation software solution, we tried to be as cheap as possible, use only the hardware we need. But of course, we also did demos and experiments with the Greengrass-based solutions. We run anomaly detection directly on the Greengrass core using the ST-based board. And we used this convolutional autoencoder algorithm. So yeah, but it's not a TinyML related thing. It's more of HTML.
Okay, awesome. Thanks for that. Yes, we have about 10 questions here, Constantine, which is great. So we'll try to get to as many of them in the time we have left. The next question is from Athanasios Bahumis, which is what are the time requirements, constraints for the response? I believe this was your demo number 1. The question's asking about.
Could you repeat this question, please?
The question is, what are the time requirements / constraints for response in your first demo?
So we see the anomaly within 1 second after it happens, I think, but we don't have any response requirements there because it's just a demonstration solution, and we are talking about the development kit for anomaly detection, and it would greatly depend on the actual use case you would like to use this anomaly detection kit with.
Cool. Thank you. Next question here is from Jeffrey Urban. It's how does the random cut forest deal with shifts in behavior of the population and its individuals over time? That may not represent a failure risk, but maybe wearing in for a population that started new. And I think, Jeff, in this question, you also put some references to some different types of car engines that were used, already kind of worn in for some kind of, reliability benefits. So if you understand the question, Constantine, it's about how they're dealing with the random.
I think it would be great to answer this question in form, because I think it's quite a difficult thing to discuss.
Okay.
Yes.
So perfect. Yeah, that question can be put into the form and it is open for discussion. So thank you for that, Jeff.
I'll be glad to answer that.
Yeah, exactly. And I guess related to this question, to generalize, how to bootstrap a reliability bathtub curve given a new population of equipment, which is a really good consideration, and that can be put into the forum. So the next question we're going to talk about is the is from Amir Hossein Molemi, which is it a battery-based system or supplied with power lines? I think that was for you. There we go.
It is supported with power lines, because usually this industrial equipment is main powered, and we have access to this power. So yes, we don't have any energy constraints here.
Okay, makes sense. So next question about the autoencoder. The question is the input of the autoencoder a KPI of the signal, like mean, standard deviation, etc., or is it the signal itself?
I would say that we right now use mean. We use the time window of means within some predefined interval, for example, 1 second. We sample it with, I don't remember the exact frequency, then we calculate the means for each part of this time window, means and standard deviations, and then we give it to the model.
Understood. Okay, so I'll try and put these questions together. I think there's 3 of them. So from Rick Pandy. So the questions are: if you can have anomalies, when you can create, then if you have anomalies, then you can create synthetic data and validate the model. It's very difficult to do the validation. So I think the question is, if you have these anomalies, you could create them synthetically to try and validate the model. That's the first question.
You can also always use statistical methods. You can try to find the distribution of the data and create some data out of this distribution. That would be a great synthetical test for anomaly detection model. But to do that, you would need to really understand the distribution of your data. It's not always a simple thing to do, especially if you have multiple modes with different densities.
Yeah, absolutely. So that's about trying to capture statistical properties of the data. The next question is this deployment possible with Mbed OS?
Yes, it is possible whenever you have access to TensorFlow and C++ on your device. It doesn't depend on OS at all.
Yep. Okay, I think you mentioned that. And then the relation to that, so the C++ library you just mentioned, it has support for custom layers designed using TensorFlow and TF Lite models?
Right now, no. Right now, we support only fully connected layers. Usually, that is enough for most applications, because the heads of the models are usually fully connected. You have different types of layer in the backbones, and we don't touch it. So if you want to support such models, you will. But as I already said, there are different use cases where you would prefer, for example, using convolution autoencoder, and this would require different types of layers in the head. And this is what we would like to add next to the library.
Totally. That'd be a great addition. So 2 more questions here we have in the Q&A, and if you have something in the chat, please put the Q&A so we can bring it up and put it in the forum. We'll try to get to as much as possible. Question is from Stephen Hernandez. It's, could you repeat the name of the C++ library that was used for backprop? Was it open source?
Eugen.
Could you type that? Just spell it out for me quickly.
Yeah, I'll try it.
Okay. Yeah, perfect. So that way we can have that here for everyone. That's a great question, and it's pretty cool.
I suppose I have some problems with accessing the chat. So could you please add this question to the forum, and I will. Sure.
No problem. That's great. Okay, we'll do another question here from Anton Sebergs, which is, did you have any issues with limited RAM on the MCU? That's a great question.
No, basically this is a very small model. It took about 10 kilobytes of RAM and several dozens kilobytes of flash. So we had enough resources to do that.
Okay, awesome. And we'll do one more question here that I see from Ahmed, which is about the backprop again. So how is the backpropagation implemented in terms of memory footprint, data transfer, data types? And how about when you're switching from one device to another, is your schema being optimized accordingly? You know, fine tuning of quantized models, etc. So this is, yeah, that's the question.
Okay. About the, I cannot readily answer about the RAM requirements for backpropagation. It's about the same as with forward pass. It don't require more than a couple of kilobytes of RAM, but I need to check that. And I'm not really sure that I understood the question about different types of device. Could you please explain it in a bit in more details?
Sure. I can try to add here. This will be the last question we address. So it's when you're switching from one device to another, are you optimizing your training scheme accordingly? You know, are you fine tuning models if they're quantized? I don't think you're doing quantization yet. You mentioned that
we
was
don't have quantization yet. We only are going to add this.
Okay, perfect. Well, that's it for now. So thank you very much for everyone for all your questions. That was really engaging. As a reminder, we'll have these brought up in the forums, the TinyML forums that are linked here. So now we're going to get into the outro part of the slides. Just a reminder. So thank you again, Constantine. And here's your contact.
And yeah, you can contact Joseph or Gennady for any business-related questions, and me if you have any technical questions.
Perfect. So there's the emails there. You can see. Also, we can put those in the chat for everyone. So please take the 5-question poll. It's super quick. It's already been shared now in the chat. You'll see that have come up during the talk, and you can continue the conversation at the TinyML forums. Again, thank you to all the strategic partners for making this possible. There are additional sponsorships available, and you can contact Olga for more information. For the executive strategic partners, we have ARM AI powering TinyML innovation with the ARM AI Virtual Tech Talks, Edge Impulse, the leading edge ML platform, Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous, Sentient, end-to-end deep learning solutions for TinyML and Edge AI. We have the Platinum strategic partners, DeepLight, which is the fastest video analytics solutions on ARM CPUs, Klika Tech global IoT solutions, Reality AI, add advanced sensing to your product with Edge AI TinyML, Renaissance, broad and scalable edge computing portfolio. For the gold strategic partners, we have Thoda Hub, Maxim Integrated, Latent AI, Micro AI, NXP, Seed Studio, SensiML, ST Micro, Synsense, and the silver strategic partners here. Reminder that the next TinyML talk is on Tuesday, March 15th. We have Matthias Hertel, product specialist at ARM, talking about accelerating ML development with cloud-based ARM Cortex-M models. That'll be at the usual time, 8 a.m. Pacific. If you're interested to present a talk here like you saw today, please contact the talks at tinyml.org if you're interested. So this is here where we'll stop. Thank you again, everyone. Constantine, that was a fantastic presentation. Love the demos, and awesome everyone for all your questions. That really was super engaging, and we can keep this going online. Thank you.